All right. So we're going to get started. So first, I want to just introduce Jake Seel real quick, who is our seminar speaker today. So Jake is a postdoctoral fellow at Harvard University in the Earth and Planetary Science Department. Before that, he did his PhD under David Romps at University of California, Berkeley, in the same name department, I believe, as well as he did his undergraduate degree at Haverford University in Pennsylvania. So Jake is originally from Illinois, but as you can see, has kind of gone crisscrossed back and forth through the country. So who knows where he'll end up next, but if I had to guess on the trend, I would say the West Coast. But Jake is going to talk to us a little bit about a lot of the work he's been doing, kind of focusing on atmospheric physics and trying to understand kind of the fundamentals all the way from theory through using numerical simulations of a different hierarchy to explore some of the most important questions in climate science related to kind of climate sensitivity, clouds, and circulation. So I'll turn it over to you, Jake.
Thanks so much, Kevin. Yeah, it's really great to be here in person. I guess, believe it or not, this seminar was supposed to happen April 1st of 2020. So it's a long April Fool's Day joke. A year and a half later, here I am. But I guess the upside of the delay is that I get to tell you about what I've been working on during my postdoc, which is mainly focused on super warm atmospheres. And I guess super warm is not a technical term, so I want to give you some context for what I mean by that. Just for context, this past summer, there was a heat wave in the Middle East where temperatures reached about 50 degrees Celsius, 325 Kelvin, 125 Fahrenheit. So this type of temperature occurs in the climate system today, but it's not an average. So my definition of a super warm climate is essentially one in which this type of temperature is sort of a mean typical temperature for the tropical oceans. So it's really way warmer than we experience now. And the point of my talk is not to scare you. We're actually not expecting temperatures that warm in the next century. But I think there are a couple of very good reasons to study super warm climates anyway. So a few of the things that motivate me. One is if you take a broader view, not just the next century, but look at all of Earth's history and even its future, super warm climates are definitely a part of the story. So we actually evolved in an anomalously cool period of Earth's history when there weren't polar ice caps on Earth's surface. But if you go back over the past 500 million years, most of the time, there were no polar ice caps. CO2 levels were much higher, and these were super warm climates, and actually going back even earlier as well. And if you look to the future, we know that the sun is getting brighter at a rate of about 1% every billion years. So, sorry, every 100 million years. So a billion years from now, the sun will be 10% brighter than it is now. That will almost certainly push Earth into this super warm climate regime. Now, a second good reason to study super warm climates is that we know that in our simulations of convection of climate today, the representation of convection is one of the biggest sources of uncertainty and confusion. And one of the things that's challenging about modeling convection is that we only have one example to learn from. We have just contemporary Earth to learn from. And so if we want to build a robust and general theory for convection that will work in warmer climates and cooler climates, we need to study climates that are actually quite different from our own to build that robust understanding. So this motivates me as well. And finally, I'm personally motivated by exoplanets. We've discovered just a tremendous number of planets, and some of these planets we'll be able to characterize with transmission spectroscopy in the near future. And if we want to understand and guide those observations, we need a general theory for how super warm atmospheres behave. Many of these planets that we've discovered are orbiting quite close to their stars and are going to be in a super warm climate state. So all of these things, for me, motivate the focus on super warm climates. So let's start to think about super warm climates. What really distinguishes them from our climate? And I would argue that it's not so much the heat, but the humidity. As long as you have a reservoir of liquid water on the surface, as the atmosphere warms, the saturation vapor pressure increases, and the atmosphere is going to fill up with water. So this is true on Earth. And we're going to look at some of the consequences of all that additional humidity, primarily on radiation. So radiation affects every other aspect of the climate system. So the way that water vapor affects radiation is that it's a very important greenhouse gas. It has these very broad absorption features that absorb infrared over a large portion of Earth's spectrum. And so in Earth's current climate, with the current amount of water vapor that we have, most of the wavelengths are blocked off except for this gap. there's a gap in the infrared absorption spectrum called the water vapor window. And through this window, the Earth can send radiation directly out to space. This is actually crucial for remote sensing. It's crucial for the cooling of the climate, the stability of the climate. But the problem is, as you add more water vapor to the atmosphere, that window shrinks. Some of those weaker absorption features start to become optically thick and also get blocked off. And for enough water vapor, the window closes entirely. So this, to me, is more than any particular temperature threshold, the main distinction between the climate regime we're in and super warm climates. It's whether that water vapor window is open or closed. So really the point of my talk is to think about some of these effects of having a closed water vapor window. And there's a number of them that might come to mind. For one thing, what's the stability of the climate when the window is closed? We know that when you force the system with solar forcing or increased carbon dioxide, it needs to be able to send more radiation out to space by warming up. But when the window is closed, how does it do that? And the surface can't see to space. So how does the system remain stable? Are you in a runaway greenhouse state as soon as the window closes? That's an important question. And that'll be the first part of the talk. And the second part of the talk is about the effect of a closed window on clouds and rain. So clouds and rain are connected to radiative cooling because energetically the heat that's released by rain is balanced by radiative cooling. And so when you don't have radiative cooling in the lower troposphere, when the window is closed, how does the radiative convective energy balance work in the atmosphere? So that'll be the second part of the talk. And I should say before we get into the meat of this, if you have questions, please interrupt it. Do not mind interruptions. In fact, I like them. So the first part is about the climate sensitivity of super warm atmospheres. And it's based on this paper that came out this year in Geophysical Research Letters. Wrote it with Nader Jeevanji, who gave a talk here a couple years ago, I believe. So we're thinking about ECS, equilibrium climate sensitivity. And we most often think about this in the pre-industrial context. You take the pre-industrial Earth, surface temperature of around 288 Kelvin, you double the carbon dioxide concentration, you wait for it to come back to equilibrium, that's the ECS. But the ECS is state dependent. And you can see that there's actually some curve like this that relates the amount of CO2 in the atmosphere to the temperature. And if you know this curve, you can find the ECS at any point along it by just doubling the CO2 and finding the corresponding warmer surface temperature. So you can do that for a cold base state. You can do it for a warm base state. And although we don't know that curve for the real Earth, we can study this in models. And a number of people have looked at the state dependence of ECS in models. And they find something really interesting. So the x-axis here is the surface temperature. And the y-axis is the equilibrium climate sensitivity at that temperature. So you see a significant state dependence where it increases from between 1 to 2 Kelvin at low surface temperatures up to a peak of over 5, and then it comes back down again at very highest surface temperatures. There's a few comments in the chat. Can anyone check those? Yeah, they can hear me. Everything good? Okay, great. So there's this peak, and this paper was my PhD advisor, David Broms's, in a cloud resolving model, but he was not the first to see this peak in ECS. It was actually found in models across the hierarchy. There was 1D radiative convective models that showed this. A couple of GCMs showed this as well. So there seems to be something robust going on where there's a point in the Earth's state where it's most sensitive to carbon dioxide forcing. And that's the point of this talk, is to understand that peak in ECS. So since this exists in models across the hierarchy, it really makes sense to start with physics that's present in all of these models. We start with the simplest model. And I really don't have to justify this anymore because this model won the Nobel Prize last week. I don't know if you saw this, but it's a very early radiative convective model. And that's basically what we're using in this study. In case you haven't used one of these in a while, this is how it works. It's an assumed moist adiabatic troposphere. It's a one-dimensional model. Isothermal stratosphere, so it's super simple. And then for the radiative fluxes, we're using a line-by-line radiation model. So we get the full spectral information that you could need to really understand how LLR is changing in different regimes. And we perform a top of atmosphere energy balance to get a equilibrated state over a wide range of CO2 concentrations. And this is that curve that then allows us to find the ECS at a given state. And when we do that, this is what comes out. again, a big peak in ECS at a surface temperature of around 310 Kelvin. So there's a point where the Earth is most sensitive to doubling carbon dioxide. And this is exactly what we want. We can dig in and understand why this is happening. So you may be familiar with this forcing feedback framework. It's often a starting point for understanding ECS. You can understand ECS as the ratio of the forcing from doubling carbon dioxide. That's how much reduction in OLR you get when you double CO2. So you take the ratio of that to the feedback, which is how much additional OLR you get when you warm the system by 1 degree. The ratio of those things tells you how much you have to warm to get back to equilibrium. And that's what I'm plotting here. So on the left, I have the forcing, in the middle is the feedback, and on the right is that ECS. So what you see is that the forcing increases monotonically across this range. So it really can't be producing this peak. It has to be coming from the feedback. And indeed, you see in the center panel that there's a minimum in the feedback, right at the same temperature that that peak in ECS occurs. So a minimum in the feedback means that there's a point where the OLR is least responsive to surface warming, where you get the least amount of additional emission when you warm the system. So that's what we have to understand. And the way we figured this out was looking at feedbacks through a prism, basically looking at the spectral information that we get from our radiation model. So to calculate spectral feedbacks, we first calculate the spectral OLR for a base state, and then we add a 1 Kelvin surface temperature perturbation and the associated moist adiabatic warming in the atmosphere, recalculate the OLR, and then take a difference. And so that's going to highlight where in the spectrum you get additional outgoing long-wave radiation when you warm the system. So it's a spectral view of the feedback. And we're going to look at a lot of plots like this. So I just want to orient you a little bit. So what I'm plotting in the dashed line here is the surface Planck feedbacks. So this is what you would see if you had a transparent atmosphere and you warm the surface by 1 degree. You would see that spectral signature there. It's just the Planck curve. What you actually see is that black thick curve, and that's reduced from the surface Planck feedback due to the presence of greenhouse gases. And there's really only 2 in our model. There's water vapor and carbon dioxide. So we can associate features that you see here with those greenhouse gases. So to me, the most obvious feature that you see is exactly this water vapor window that I mentioned in the introduction. This is the part of the spectrum where water vapor doesn't absorb and really no other gases do either. And so the feedback is strongest there because the surface can see almost directly out to space. So you come closest to that surface Planck curve. Now, outside of the water vapor window, the feedback is really suppressed, almost 0. And it's worth wondering, why is the feedback so small there? When you warm the system, the whole atmosphere warms up. So why don't those optically thick wavelengths also send more radiation to space? Why is the feedback so small? And it really comes down to how water vapor works as a greenhouse gas. So this is a little bit of radiative transfer physics, but it's just a little bit. When you look down from space at the Earth at a wavelength where there's a greenhouse gas doing the absorbing, you don't see the surface, you see what's called the emission level. So this is where the optical depth is around 1. And for water vapor, the concentrations of the greenhouse gas, and therefore also the optical depths, are approximately determined by temperature. They are a fixed function of temperature. And as a result, when you warm the system, a given optical depth of 1 level occurs at the same temperature, just higher up in the atmosphere. So it doesn't change its temperature, it just shifts up in altitude. And that's a situation where you get no increase in outgoing long-wave radiation at that wave number because it's got the same emission temperature. So this is actually the basis of the water vapor greenhouse effect, is that you don't get this additional OLR once the CO2 is optically thick, sorry, the H2O. This physics goes way back to 1928. It was realized by Simpson, and then recently a nice discussion of this Simpson's law, which is that the OLR does not respond to warming once it's optically thick, is in this paper from this year by my collaborator, Nather. So that's the water vapor part of this curve. But there's this other really interesting feature in the spectral feedback, and this occurs right around the absorption band of CO2, the 15 micron band. And here you see these twin peaks in the spectral feedback. And these are actually very interesting because they seem to be enhancing the feedback beyond what you would get with just water vapor. And that's a little counterintuitive. How can adding an additional greenhouse gas give you more spectral outgoing long-wave radiation than without it? Well, we have to think about what's different between CO2 and water vapor. And the main difference is that carbon dioxide is well mixed in the vertical, so its concentrations are approximately uniform, rather than being condensation limited. That means that its optical depths and therefore its emission levels are fixed functions of pressure, not temperature. So when you warm the system, the emission levels stay at the same pressure, but they warm, and so they send more radiation out to space. That's in really stark contrast to how water vapor behaves. And so this is exactly why you get that radiator fin behavior. So that may have gone by a little quickly. I'm going to summarize those arguments here, but this is a really key concept. So are there any questions about this radiative transfer idea? All good? Everyone's on board? Cool. So now we're going to look at how this feedback evolves over the range of surface temperatures that we probe. And in each case, you're going to see the water vapor window highlighted in blue, the CO2 radiator fins, where the emission is enhanced by CO2, highlighted in red. And then on the right is the total feedback decomposed into those two contributions. So this is an animation, and I hope this plays on Zoom as well. Can we get a confirmation of that? It does? Cool. I'll play it again. But you see that there's really a regime transition. So at the cool surface temperatures, let me get right back to the beginning. At the cool surface temperatures, which have low CO2, feedback is really 100% due to the water vapor window. As the temperature starts to increase and the CO2 increases, the water vapor window shrinks and the CO2 radiator fins grow. And then at a certain point, the water vapor window is closed entirely. So there actually are no wavelengths where water vapor is not optically thick. But in its place, the CO2 radiator fins have grown to be incredibly strong, and they have totally picked up the slack and are now almost entirely responsible for the feedback. And you can see that in the decomposition on the right, that the CO2 radiator fins are doing all of the lifting for stabilizing the climate. So I think the takeaway message here is that there's sort of a two-part relay for stabilizing the climate. At cool surface temperatures, the water vapor window's doing it, but they close. And in fact, if they were the only greenhouse gas, you'd be headed toward a runaway greenhouse state where the OLR is not responsive to surface warming. But instead, they pass on the baton to the CO2, which picks up strength and carries things across the finish line. So you get this minimum in the feedback and the peak in the ECS right at the trade-off point between these two mechanisms for stabilizing the climate. Now, one aspect of the story that I haven't gotten into is why those radiator fins become so strong at high surface temperatures. There's really two contributions. One is that besides the 15 micron band, there are additional weaker absorption bands of CO2, those second sets of spikes that you see showing up. So those show up at high CO2 and contribute. And then the other factor is that when you have warming on a fixed pressure level, which is moist adiabatically controlled, it's much enhanced at very warm surface temperatures. So you get huge upper tropospheric amplification of the warming, and that's what's warming the emission levels and causing them to emit more radiation to space. So basically, moist adiabatic physics also gives you a really big increase in power for the radiator fins. Cool. So just to summarize the first part of that talk, we saw that even when the window is closed, the CO2 radiator fins can stabilize the climate and prevent you from being in a runaway greenhouse state. So this is sort of like a positive thing that CO2 does for the climate system. It actually stabilizes it in super warm climates. Now for the second part of the talk, we're going to turn to this question about clouds and rain. How do they respond to the closing of the window? And let me just remind you how these things are related in the current climate. So I've got a schematic here of the troposphere, and throughout the troposphere, you have radiative cooling, so emission of infrared radiation to space. And in a time mean, that is balanced by convective heating, primarily latent heat that's released in precipitating clouds. These two things are in balance. That's called radiative convective equilibrium. Again, that was the model that won the Nobel Prize recently. So this is sort of basic climate physics. And if you look at the decomposition of that radiative cooling, you see it's actually the sum of two terms. One is the long wave cooling, which is the infrared, and then there's also a radiative heating. There's some shortwave radiation that's absorbed within the troposphere. And so there's a small amount of radiative heating, but it's smaller than the cooling, and in the net you get that radiative cooling. In contrast, we look at a super warm climate state. When the water vapor window is closed, the lower troposphere can no longer see to space. That means that there's no infrared cooling there. But the weaker absorption features in the near infrared and the short wave are still active. So you actually still get short wave absorption in the lower atmosphere. So in this situation, in the super warm climate state, you actually get net radiative heating above the surface in the lower atmosphere. This should have some really big effects on the climate, because the climate is used to having just radiative cooling that can be balanced by latent heating. So understanding what this does to the climate system is mainly the point of the second part of this talk. And this actually connects back to some lingering questions I had from the first part, because when people saw this peak in ECS and GCMs, they noticed that it was happening right around where the lower troposphere started to get heated by the radiation. And they actually connected these two things, because it seemed like that radiative heating was inducing this very strange state in the climate models. What happens in models with parameterized convection is that they develop these huge surface inversions. So you see the temperature increasing with height above the surface, as opposed to dropping off moist adiabatically like it does in our climate. And associated with that transition to the new state with the surface inversions, there was this region of really enhanced stability where the whole climate system rearranged itself. So this is a huge departure from the climate regime we're in. And the question is this really how the atmosphere responds to shortwave heating in the lower atmosphere? I think you have to take these results with a big grain of salt, because they both use parameterized convection, using simplified representations of clouds and rain and how they respond to radiative forcing. So to really understand how the system behaves, we have to use a model that can resolve convection. And that's what we're going to do. So we're going to take a closer look at convective dynamics in super warm atmospheres. This part of the talk is based on this paper that's coming out in a couple of weeks. I just got proofs for it. But it's again using a cloud resolving model to study these super warm climates. And this is really my favorite tool for research. It's a very high resolution fluid dynamics simulation. You have representations of radiation, sunlight, infrared cooling, representations of phase changes of water. And the state you simulate is just that radiative convective equilibrium here. Infrared cooling being balanced by latent heating releasing these clouds. But unlike in a GCM, all of that convective transport that provides that heat is explicitly resolved. It's not parameterized. And for that reason, it's really more trustworthy in unfamiliar regimes. Right? Unfamiliar regimes is exactly where you shouldn't trust convective parameterizations. You really have to go back to the basics and use the physics equations that we know. So just to help convince you that these simulations are somewhat realistic, this is a comparison of satellite image, tropics today, surface temperature around 90 Fahrenheit. And the right two panels are the simulation outputs. You're looking down from space, and where you see brightness, that's a lot of reflected shortwave, that's cloud cover. And as I play this, you see the clouds bopping around. They're producing rain, which is at the lower panel here. And it's in a sort of quasi-steady state. It's always raining somewhere. It's moving around, sloshing around. But you see actually a lot of the same cloud morphologies. You see, like, if I can pause it, see these dissipating cloud anvils that are surrounded by clear areas, and then shallow rings of new triggered convection from cold pools. Same thing you see in the satellite image. So they really capture something fundamental about the tropics. Now the question is, how does this state behave when the system is much, much warmer? One way to make a much warmer atmosphere is just to increase the brightness of the sun, take a simulation like that, let it re-equilibrate, and see what happens. So that's what we did. And the new surface temperature is 135 Fahrenheit, super hot. It definitely qualifies as a super warm atmosphere. And on the right again is the cloud cover and the rain from this super warm atmosphere. So I'll play this. What you see are swirling clouds, but actually no rain. There's no rain accumulating at the surface until all at once, this huge outburst of clouds and rain. It's like a Jackson Pollock painting. Suddenly, a ton of rain on the surface, and then it goes back to being quiet. And the clouds swirl around, developing, still no rain at the surface. And then all at once, boom, another big outburst. And this just repeats like this over and over. Every couple days, huge outburst of rain. If you look at the time evolution of this state, starting from the initial condition, surface temperature of around 305, it's current tropics today. That's when we increase the brightness of the sun at 0, surface temperature starts to increase. And you see that right around 320 Kelvin is where you start to get these big spikes in precipitation, this regime change. Zoom in on surface temperature or near surface moisture energy or the precipitation, you see the difference in these regimes. Our climate regimes in this quasi-equilibrium regime, we get noisy fluctuations about the mean. Whereas the super warm climate regime is this relaxation oscillator regime. So the near surface moist static energy goes through long periods where it's recharging, increasing, and then suddenly there's an outburst of precipitation that drops and then it goes through again. Actually build a circuit that does this. It's like a charge a capacitor and then drop, charge a capacitor, and then drop. So this is the difference between these two states. Now, just for context, how much rain is really released in these outbursts? So this is approximately to scale. Comparing this to the rain totals from a tropical cyclone that made landfall. So you're getting a couple hundred millimeters of rain that's released in pretty large areas during these outbursts. It's comparable to a glancing blow from a tropical cyclone. And I guess the difference is that this happens every couple of days, so it's really not a rare event. The norm for rain is these huge flash flood-inducing downpours. So that's what happens. Next question is, why does this happen? Now, going into this, we had a suspicion that it was the radiative heating that was going to cause a big change in the climate system. So just to confirm that that's the case, we did some fixed SST simulations. The closing of the window is fundamentally tied to the amount of water vapor, which is tied to temperature. So you shouldn't have to increase the brightness of the sun to get this to happen. You should just be able to increase the surface temperature and get the same thing. And that's what we saw. So these are the increased surface temperature precipitation time series. And you see, again, the development of this episodic regime around 320 Kelvin. And the radiative cooling grades are shown in the upper panel. You see it's the ones with the radiative heating that get into this episodic regime. So that's suggestive, but not conclusive. We could do mechanism denial tests to really nail this down. So we prescribed some radiative cooling profiles that don't have this lower troposphere radiative heating. And when you do that, you see steady convection at all surface temperatures. So it's not the temperature so much as the radiative heating profile that you get naturally in warm climates. And the converse of that, if you prescribe radiative heating, you can get this episodic regime in any surface temperature you want. So it's really the presence or absence of radiative heating in the lower troposphere that drives you into this episodic state. But why does it do that? Why does it cause this outburst regime? So here's just sort of a schematic of what's going on. As we know, the sun evaporates water from the surface, but in super warm climates, it also forms an inhibition layer. It heats a layer of the atmosphere above the surface that is convective inhibition, prevents the evaporation from the surface from getting up into the upper atmosphere. It's sort of like a buoyantly, buoyant cap on the near surface layer. And just as an analogy, you can imagine boiling water on a stove and putting some sort of non-conductive barrier in between the bottom and the top. So this is a very convectively unstable state. So you've built up a ton of light fluid at the bottom and cold dense fluid above. If you somehow remove the barrier, all at once you'll get really vigorous overturning everywhere in the pot. And that's exactly what seems to be happening in our simulations. But what removes that barrier? What is it that removes the inhibition? It turns out it's a particular type of cloud, virga, really type of precipitation. So you may have seen these, they look kind of like jellyfish. Virga is rain that evaporates before it hits the surface. And these play a really key role in super warm climates. This is a schematic of what's going on. So during the recharge phase, when there's no surface precipitation, you have surface fluxes accumulating in here. You have this radiatively heated lid keeping everything trapped. But in the upper atmosphere, you still have infrared radiative cooling. So this part can reach condensation, reach the condensation point, and form clouds, and they rain. So that rain just falls and doesn't make it to the surface, evaporates somewhere up here. So that's the virga. Now, as this progresses, there's the virga again. You can see during that animation, there was all this cloud cover, but no surface rain. So that's all virga. Eventually, that elevated convection layer drops to low enough in the atmosphere that the virga actually starts to evaporate within the radiatively heated layer. That evaporative cooling suddenly removes the lid, and that's when you get the triggering and this big outburst of deep convection. And this really is a chain reaction, because once you have deep convection forming cold pools, you have all of this juicy air down there at the surface, and there's no lid, so it just goes off like a bomb. This is the three phases of this regime. And if you want to see that in real data from the simulations rather than schematic, this is what that looks like. So the top panel here is the cloud mass flux. So where you have cloudy air moving upwards, we call that convective mass flux. And you see that during the recharge phase, what I've highlighted in green is the elevated convection. So there's no surface convection making it up into that layer, but you have convection in the radiatively cooled layer. And you see that it's producing precipitation, that's this panel. But this is the virga. It's evaporating before it hits the surface until the triggering phase, when it makes it into this radiatively heated layer, which is below this dashed line. And you get this evaporative cooling. That's the blue. That suddenly reduces the inhibition. As you can see, the potential temperature there suddenly drops. There's no lid, and you get this big outburst of surface rain, the reduction in the convective instability, and this just repeats every couple of days. So what are some of the implications of this novel regime? Well, one very basic thing is, what is the effect on the temperature profiles? We were motivated by those big inversions that we saw. And in our simulations with these solid lines here, you see that there are no surface inversions. So the episodic convection happens every couple of days, and that's able to keep the system approximately moist adiabatic, even in the super warm state. Now that's with the normal configuration of the model. We can actually reproduce that surface-based inversion state if we turn off evaporation of rain. So you can go into the model and just say rain doesn't evaporate, it falls straight to the surface. And if you do that, you no longer lift the lid, and you form this weird state with a huge surface inversion, dry adiabatic layer, and the moist layer further up. So this is what the GCMs do. And I think this is really suggestive, because we know that the GCMs don't simulate this state that we got. And I think this could be the main reason, is that their convective parameterizations are not dealing with rain evaporation correctly. It's not something that's thought to be that important in the current climate. Some models just drop rain right to the surface. Some do have some representations of evaporation. But I think this is actually a really good example of how studying an exotic climate can point you toward a way of improving a convective parameterization. This is some missing physics that causes them to produce potentially a very wrong state in warm atmospheres. And it really could have implications for simulating smaller amounts of global warming too. So an avenue of future work definitely is to try to make a convective parameterization that has rain evaporation in the right way and can reproduce this episodic regime. And that may very well change the super warm climate state in GCMs pretty significantly. Now, another effect is on cloud cover. You actually see a huge increase in upper tropospheric, in particular, cloud cover in the oscillatory state. It goes up by a factor of almost 3. This is associated with the elevated convection in the recharge phase. It's very cloudy and very reflective and very insulating. So as you might expect, a sudden increase in cloud cover has a big effect on the stability of the climate. We're looking here at the feedback at a range of temperatures, and a positive feedback in this plot means the system is unstable. So it means that as you warm, you absorb more energy. So that will cause you to keep warming, and it's unstable. So what we see is actually a transient instability. If you look at the all sky fluxes in black, there's, during this transition, a period when you kind of fall off a cliff of stability. You go up to a warmer temperature until you get back to a stabilizing feedback again. So it's a brief and transient instability as the system rearranges itself. And you also see that in the clear sky fluxes, smaller in magnitude, but the cloud feedbacks, you can see the long wave and short wave are really big contributors to this regime transition. And it's something that has to be checked in global models to really believe in it. Now, as mentioned, motivation by exoplanets. And here, an interesting fact is that many of these exoplanets around M stars that have stellar spectra that are shifted towards the near infrared, more red light. And that's exactly what's absorbed by water vapor. So that should increase the absorption of shortwave and should make it more likely to trip into this regime of episodic rainfall. And so we did some simulations with an M-star spectrum, and we see indeed that the episodic regime comes in at a cooler temperature. So it's easier to trip into that state for a given temperature. And I think one of the big geological implications of this is the fact that rain does surface erosion and weathering. So we know that the erosion is really nonlinear in the intensity of rain. If you have the same amount of rain that comes in one flash flood or in a week of really light drizzle, you get way more weathering when it's the flash flood. And so this future regime where basically all rain occurs as intense flash floods is going to really accelerate your surface weathering. And this has implications for the long-term stability of climates because there's this silicate weathering feedback that regulates the amount of CO2 as you increase the surface temperatures. This is a real strengthening of the silicate weathering feedback. In super warm climates, potentially they really are able to draw down CO2 from the atmosphere. It also has implications for interpreting geological features on other planets. If you look at Mars, that has these valley networks, and a big question, we know that there's no water on Mars today, but at some point in the past, there must have been warm and wet climates that were able to form these features. But we don't know how long they would have had to exist to carve something like that. And our work is suggesting that it could actually be significantly shorter than we thought if the rain is occurring in this really intensely episodic regime. Now, just the last sort of fun connection I want to make here is to the idea of spontaneous synchronization. So this is a phenomenon that happens in a lot of areas of the natural world, where you have a bunch of individual units that are sort of oscillating in some sense, but they're out of phase, so they're unsynchronized. And one of the most famous examples of this is fireflies. Fields of fireflies can start out unsynchronized like this, but under certain circumstances, they can become globally synchronized and all flash in unison. And you can see that this is very analogous to the state regime change that we saw. So this unsynchronized state is sort of like the tropics today, where you have convection happening here, rainstorm popping up here, but they're all out of phase and they're not really connected to each other. Whereas in the future, they all convect at once because they are suppressed and they all release their instability at once. So this sort of regime transition is, I think, the first time it's been observed in the atmosphere. And just to push it a little further, you can actually make a two-layer model with convective oscillators that are sort of like those fireflies, but they are somewhat sensitive to what their neighbors are doing. And if you increase the inhibition, that two-layer model goes from a quasi-static state to this episodic state. And the same thing you see in the cloud resolving model. You switch the radiative cooling profile from radiative cooling to radiative heating, you get this transition. So it's actually a mathematical analogy as well. All right, so that's the second part of the talk. So we saw that lower tropospheric radiative heating causes this intensely episodic rainfall regime. And that really means that we need to revisit the simulations of super warm climates with GCMs. So I just want to thank my collaborators. So on these two papers, first one is Nader Jeevanji, he's a scientist at GFPL, and the second one is my postdoc advisor, Robin Wordsworth. And both of these papers are going to be available. This one is available now, and this one will be available in about 2 weeks. And with that, I'd love to take some questions. Thank you very much.
All right, so we have time for some questions, and then I'll keep an eye on for those that are listening, you can either raise your hand or ask a question in the chat. But first we'll take some in the in-person audience. So Levi.
Local files and talk about how there could be, the window closes, then there's really close to the shortwave. It's not able to long space. Yeah. Curious how much local files could get all the way to the surface and function as a way of the lower troposphere actually cooled in a way that seems like a lot of models don't capture the back of the plate work.
Right, so I guess.
Can you repeat the question or part of the question so that we make sure they hear?
Yeah, Levi's question is, could clouds in the lower troposphere provide a certain amount of radiative cooling, not by cooling to space, because they're also blocked by the window, but by cooling to the surface? And I think that for that to work, you'd have to have a pretty strong inversion. I mean, they would need to be warmer than the surface for that to be a cooling term, that exchange. And I think that's just not the case in our simulations, correct? That they fall off quite quickly back. I think their cooling is to space or not. But maybe we can talk about that more.
The clouds then warmer than
They would need to be in order to provide a cooling, but I don't think they are cooler than the surface. Yeah, so they're actually heated by the surface.
Yeah, so Mingwao.
Yes, so you mentioned that the GCMs cannot generate this episodic convection, and you said it's the rain evaporation that's not correctly simulated. I think it's more than that because GCMs have this hardwired cape criteria. Once you have instability, then convection will happen. That's probably why I say the models drizzle too much, but the rain intensity is not as. So this is very interesting.
Yeah, that's a very helpful comment. I guess I think that I agree that they're too eager to convect now. In the future, in the super warm climates, it seems that they're not producing surface-based convection. So that to me suggests, even though there is tape in that state, there's such a large layer of convective inhibition that's preventing them from triggering a surface-based convective adjustment. And so they trip over into this other regime. So they must be sensitive in some sense to that inhibition because they're not producing surface-based convection when they should be.
Yeah, many models just do surface-based deeper convection, but some models do allow convection to initiate above the surface. So I think the cloud resolving model really is the way to look at the model.
But do you think it should be possible to build a convective parameterization that does this? I think it should.
That would be very hard because you just have this much information within this large grid. So you do not have the subgrid dynamics to really drive the convection. I don't.
Maybe a bad idea, but I'm going to try.
Well, so the other aspect of that is in the CAPE calculation for the trigger in those convection schemes, right? That they have a limit on the number of inhibition levels that are allowed for the CAPE calculation that's used for the trigger itself. And so you could see in these type of settings that it likely the CAPE calculation would actually be wrong to some extent because it would be capped right at the boundary layer or something, and it wouldn't be able to even calculate a high enough CAPE to trigger.
So it will be actually interesting to understand why say convection does not occur in your case when there is a CAPE if the branch level is above the surface, and under what conditions that convection would be triggered.
Yes.
in the cloud resolving model.
Yeah, it's a great question. Let's see here.
Yeah, this is very interesting. It's
So you
like-
see, there is convection. It's just it's not able to penetrate into the upper troposphere. So it's some combination of being dry and stable that shreds their instability and prevents them from getting up.
And there are convective parameterizations with evaporation. right?
Yes.
Yeah. They were developed for NCSs to get school food.
Yeah, so here it's like a convection is expanding in both directions, going up, going down, and then.
Yeah, although I would emphasize the top-down control. I mean, to me, there's not much special going on down here when the triggering happens. But the recharge is definitely happening. The air is becoming incredibly moist and humid. Yeah.
Well, it's also interesting because, in advances in some GCMs and convection schemes has been the inclusion of evaporation of rain particularly differences between CMIP5 and CMIP6. And I wonder if that kind of gets at a little bit of some of the differences that we're seeing.
Yep.
I think Ping has a question.
Yes, on this slide, the convection that time, roughly in time, along the convection over here on this slide,
Yes.
the convection we saw here in terms of time.
Yeah.
How wide would that be?
This outburst,
Yes,
it's a few hours.
a few hours.
Yep.
So is that the only type of convection we can see in this model? In this type of setting? Is this the only convection we can see in this type of settings?
The only convection you can see.
Is there any other different convections such as we see in the nowadays we can see shallow, middle, and deep, a variety of them.
Well, there's the elevated convection, which is going on throughout the recharge periods. That's, I would say, a different type. And there is shallow, very shallow, weak plumes that just aren't able to break through the cap. So
Okay, so by comparing the convection for several hours here, the recharge time window looks like how long?
a couple days. Yeah, it's a couple days of recharge and then 3 hours of release.
Okay, so there will be either simple or complicated mathematical model to simulate this recharge, discharge process.
Yeah,
Do you have one?
I think so. I mean, I have this this two-layer model is basically each of these oscillators is behaving like that. It's being recharged by surface fluxes and by radiative cooling. So there's a buildup of cape during that recharge. And then there's a stochastic trigger that occurs. And whether it actually fires off depends on the amount of inhibition. So if you just have those ingredients, you'll get a bunch of noisy oscillators that aren't in phase. The way to get them to be in phase is to have a local coupling. They have to be sensitive to what their neighbors are doing. So it's sort of like a cold pool triggering. And so when you increase the inhibition, you go from a noisy, unsynchronized state to a synchronized state. But the individual elements are always doing the same thing, whether it's synchronized or not.
Okay, so this model is limited area.
Yes,
How large?
I've tested it in domains up to 500 kilometers on a side, but it's an excellent question because I don't know what happens at much larger scales, and I don't know how this couples to large scale circulation. So I think running something like a global SAM, so SAM actually does this. It does the same state in 325 Kelvin or so before it crashes. So I think I can run SAM and get it to do this. Yep.
So if you try to different does it produce a similar result?
Yeah, that's a great question too. That's another thing you might not trust in a super warm climate is the microphysics. So I went basically to the simplest possible scheme I could think of, which is a two-phase scheme. There's just water vapor and rain. Sorry, it's three classes: water vapor, cloud condensate, and rain. And the conversion from water vapor to condensate is just a saturation adjustment, which should work in all climates. And then there's just a time scale that sends cloud condensate to rain. And you can mess around with that time scale, but it does reproduce the same thing, even with just those ingredients. So I think it should be robust to the details of microphysics, because fundamentally they're all doing something like that, and that works.
So I think we have one question online. Can you make sure your volume is up before I call on it so we can hear it?
Yeah,
Yep, Steve, go ahead.
yeah, thanks. And hello, Jacob. I found your talk very interesting. I guess I reacted more to part one than to part two, and I have maybe more a comment than a question. I thought it was very interesting. You're separating out the in terms of the dependence of sensitivity on initial state, separating out the forcing dependence and the lambda dependence, which I think is very interesting. Separating those out, we really get a sense of that lambda dependence distinct from the forcing dependence, and really that's I think the lambda is much more indicative of the climate system response. The forcing is kind of incidental. We happen to choose carbon dioxide, et cetera. But I'm wondering if you might want to comment on what motivated you to do that.
Yeah, I mean, this, separating out the forcing and the feedback is just sort of like the standard starting point. So I thought I would start there, but I mean, you bring up a good point that the CO2 concentration is actually not independent of the feedback. And that's actually one of the main parts of the talk, or the points of the talk, is that the actual feedback you get depends on the amount of CO2 in the atmosphere, because it increases how many of these radiator fins and how powerful they are. So that, in that sense, the CO2 piece is not incidental. It's actually a key part of the story. And if you say forced with just solar forcing and kept fixed CO2, you wouldn't necessarily see the same response in this model because you don't have the strengthening of the fins. But yeah, I appreciate the comment. Does that help to answer your question?
Yeah, but I mean, in principle, we could do the same thing, say, with methane. And it might be interesting as you increase, say, the methane forcing, to what extent that lambda is reacting to that forcing as distinct from the way it would be reacting with CO2 forcing.
That's also an excellent point. I think that the physics should work with any well-mixed greenhouse gas. So yeah, methane should have the same radiator fin properties as CO2. I mean, CO2 has some advantages due to its placement in the Planck function, but yeah, in principle, methane should work too.
Yeah, I found it a very interesting way to plot it up. So thank you for opening my eyes on that.
Thank you very much.
So maybe I'll finish off with maybe one question or comment. So related to this pulsing that you see.
Yeah.
So this is kind of getting at, I think, a little bit of the question that Ping was asking about domain size.
Yeah.
So, we've seen in the past that convective aggregation in a CRM can actually be really dependent upon the domain size, particularly in non-rotating cases.
Yep.
And so I'm curious of if you think this same kind of capping and kind of, would happen in when you add rotation in, or even at low Coriolis, or right, because what we see in the real world is that one of the biggest forms of convective aggregation is actually tropical cyclones, right? And they require some amount of Coriolis force. And so I wonder if you think that we would have the same pulsing there when it's kind of a more natural way to get to aggregation, than kind of the self kind of organizing aggregation.
Yeah, that's a great comment, and it's provocative because I do sort of right now think of this state as a temporal convective self-aggregation as opposed to spatial. It's like a synchronization. I mean, the short answer is that I don't know how it will respond to rotation, but I'm going to check. I think it's possible that this state can't support hurricanes, because if the convection only occurs every couple of days and you aren't able to sustain sort of the building of the low pressure center over long periods that it takes to generate a cyclone in RCE, I'm just not sure that it would work.
Right, so you could imagine a direct analogy to a hot climate would be a case in which you can have tropical cyclones, right? The poles would be really warm, so you could actually get so much vorticity that maybe that's what you just suggested wouldn't matter. And and I'm curious, because there has been suggestions in the past and during hot climates that we've actually had a significant tropical cyclone activity near the pole. And the other analogy there, I think, is related to kind of, or interesting aspect is related to exoplanets, because exoplanets have a variety of different sizes and different rotation rates, which really determine how eddies like tropical cyclones can form. And so it's kind of this additional lens to see what role that's one of a natural way to start to see kind of what circulation can play, I think.
Absolutely. Yeah.
Okay, so with that, we'll finish up. So real quick before we say thanks to Jake, would be just a reminder, we'll have a lunch outside, and then at about 1:40-ish, there'll be opportunity for the graduate students to chat with Jake outside as well for a little bit about whatever you'd like, some more questions related to his talk, about career advice, things like that. But with that, I want to just thank Jake for coming out here one last time.